not dissolved in water. But what it tells me is limited, right? So I know I can't store it near to a flammable source, but where do I put it? Is it a gas? Is it a liquid? Is it a solid? Right? Those things I don't know. But if I know the molecular formulas, if I know the actual formula, it gives me more information. So CH is empirical. Just H and C in a 1-to-1 ratio in this particular case. More information I can glean if I knew the molecular formula. The molecular formula tells me not just which elements are present, but in exactly how much. So I know I can have 2 carbons and 2 H's. That's a molecular formula. 6 carbons, 6 H's. That's a different molecular formula. 10 carbons, 10 H's, and so on. Now, all of these have exactly the same empirical formula, right? Because if I divide across by 2, I get this. Divide across by 6, I get that. Divide across by 10, I get that. Divide across by 100, I get that. So all of these are molecular formulas. They are formulas of the actual molecules. They tell me which elements I have and actually how many, not just the ratio. So my molecular formula gives me more information. So yes, I knew that these could burn and they did dissolve in water. But now I know that's a gas because I know the actual molecular formula. It's a very light compound, that's a gas. That's a liquid, that's volatile. In other words, I could smell that. Wouldn't want to because one of these compounds is benzene, which you wouldn't want to smell because it's toxic. C10H10, it's volatile, it's not quite as volatile as this one. This will boil at around 80 degrees. That's going to boil somewhere around 120 degrees. That's much higher. That one is a solid. So the molecular formula gives me more information than the empirical formula does. So if I have a choice of which formulas I get, I would take molecular. Because I can work out empirical from molecular. Just divide across by that number. Right? So molecular formulas give me more information than the structural formula. Well, is there a way to go between them? The answer is yes. To go from molecular to empirical is dirt easy. Find the common number, divide across by it. That's easy enough. But how would I go from empirical to molecular? How would I do that? And the answer is, I will need to know additional information. So suppose somebody said to you, I have a compound of formula CH, and you will say, I know, if it's CH, it's a hydrocarbon, and it doesn't dissolve in water. And that's fantastic. Okay, good. If they give you the molecular formula of the compound, if they give you the molecular mass of the compound, you can work out the molecular formula. So here is CH, and this formula unit has a mass of 13, right? Carbon is 12, atomic number 12, H is atomic number 1. So CH is 13. So if they tell you, I have a compound formula CH, whose molar mass is equal to 26, well, there must be 2 13s in that 26, and the formula is C2H2. If they said the molecular mass was 78, well then there must be 6 of these. In other words, so it's 26 divided by 13, which is 2, 78 divided by 13, which is 6. So the formula must be C6H6. And if I said the molar mass was 130, well then there are 10 CHs, and the formula is C10H10. So I can move seamlessly between the empirical formula and the molecular formula. Molecular and empirical needs no further data. I just divide by the number. Empirical to molecular requires an additional piece of information, which is the molar mass of the compound. And I will divide the molar mass of the compound by the mass of the formula unit. Right? The mass of the formula unit. And it's always going to be a whole number. and you multiply that whole number by the numbers given in the formula unit. Okay? If we can do one more example maybe. So if I have an empirical formula of CH2O, which is the basis of your hydrocarbons, and someone says I've got a compound of molar mass equal to 180, and you're asked what is the formula, what is the molecular formula of that compound. So you will say the mass of the formula unit is 12 for the carbon, 2 for the hydrogen, 16 for the O, that's 30. How many 30s are in 180? 6. So I'm going to multiply each of these, the 1, the 2, the 1, the 1s are understood, by 6, and my molecular formula is C6H12O6. Okay? So we can move from molecular to empirical formulas. From empirical to molecular formulas with the molar mass. The third kind of formula is structural formula. And if I had a choice of all three, I would take the structure. So let me give you an example. If I tell you I have a compound whose empirical formula is C2H6O. That is the empirical formula. But you're told that the molar mass of the compound is 46. Okay? The molar mass of the compound is 46. Okay? Remember, this is the empirical formula. What is the formula unit? Well, carbon is 12, 2 times 12 is 24. Right? So 2 times 12 equals 24. 6 times 1 equals 6. 1 times 16 for the oxygen is equal to 16. I add those, that is 46. If the molar mass is 46, how many 46s are in 46? 1. So the actual molecular formula is C2H6O. And that's okay. Sometimes the molecular formula and the empirical formulas are the same. That's okay. 1 is a perfectly good number as a multiplier. But it turns out there are 2 different C2H6O species. There is this one. And there is this one. This gets to the issue of complexity and variation in organic compounds. Okay. This one, you can call it different things. Most people call it dimethyl ether. It's also called methoxymethane. This one is called ethanol. Those 2 compounds, although they share the same molecular formula and also the same empirical formula, how the atoms are connected to each other, the structure of the compounds, they vary. I have a COC skeleton with H's on the C's. Here I have a CCO skeleton with H's on both the C's and the O. Those compounds couldn't be any more different. This compound is a gas at room temperature. It does not dissolve in water. It will burn because it's got C and H's. Anything with C and H will burn. Gas at room temperature will burn. Doesn't dissolve in water. Toxic if you inhale it. And in fact, if you inhale that compound in large amounts, 2 things will happen. You will go blind temporarily or permanently, and you will die. either because your blood pH goes very low to the point where you're acidotic and your enzymes don't work, right? And your proteins start doing funny things. And as this course progresses, I will tell you why that happens, right? Because we can look at the structure of the compound and predict its behavior. So here's a compound which is a gas. Now, it's C2860. It's a gas which you will learn how to predict. Lots of exciting things waiting. It's a gas. It's not going to dissolve in water. And oh, by the way, if you inhale that, you're going to go blind or you're going to die. Okay. What about this one? This is ethanol. This is a liquid at room temperature. And it's a relatively high boiling liquid. It boils at 78 degrees Celsius. It is miscible with water. In other words, it dissolves infinitely in water. Right? It dissolves infinitely in water. And it's nowhere near as toxic as that one. In fact, people drink this on a fairly regular basis. This is the ethanol that is called alcohol, that is found in beer, wine, vodka, gin, rum, tequila, right? Blah, blah, blah. So this is drinking alcohol. So if you go to the store and you say, give me some C2860, that's not going to be good enough, is it? Because they give you this one. First of all, you can't drink it because it's a gas, right? And should you manage to do it, you're going to be blind all day. If they give you this one, well then, oh joy. On a Friday afternoon, you're watching a ball game or whatever, this is perfect. I'm not advocating for that. So the structural formula gives me more information about the compound. Yes, I can tell from this is going to be combustible, but that's about it. From this, I can say, yeah, okay, fine, it's combustible. This is not going to be water soluble. I'm going to explain why. This is going to be toxic. We can explain why. This is going to be water soluble, water miscible, in fact. It's going to be a liquid. This is something you can ingest. So the structural formula gives me a lot more information. By detailing how the atoms are connected, I can learn details about the physical and chemical properties of the compound. This is important. I can learn details about the physical properties, its boiling point, its state room temperature, its color, its solubility, and its chemical properties, including toxicity. Right? I can tell those about the compound looking at the structure. And what a power to have to look at the drawing of a compound and be able to say with absolute certainty, here's what that's going to do. Here's how that's going to behave if you do this to it, that to it, that to it. Here's what would happen if you inhale it or ingest it. Here's the risk it proposes or benefits. That is one of the things we will get out of this class. The ability to look at compounds and predict the behaviors. Because they behave in very predictable ways. Okay? I will tell you it's not surprising that water is HOH. Right? See? These two compounds have similar features, and so those compounds tend to behave well with each other. That's why the one dissolves in the other. You will notice the absence of this feature in that compound, which is why it does not do that. It does not dissolve in water. Okay? So there are lots of information that we can glean from the formulas of compounds. A limited amount from the empirical, more from the structure, but from the molecular, but a lot more from the molecular formulas. And when we give the next lecture, we talk about what are the rules that govern the ability to draw reasonable formulas for organic compounds. Very well. Okay, we'll talk about this some more when we meet on Thursday. Okay, thank you.